All right, welcome to lesson 4.7, analyzing graphs of polynomial functions. So in this lesson, our learning objective is to be able to analyze the graphs. How do we know if we can do that? If you can identify a turning point of a graph of a polynomial function, if you can explain the relationship among the degree of a polynomial function, real zeros and turning points, and if you can determine whether a function is odd, even, or neither. So that's what we're going to do in this lesson. So to start us off, they gave us a key idea. Here is something that we have been talking about. We've been talking about finding zeros. We've been factoring. We've been finding solutions. We should know where our x-intercepts are. So this one's just saying let f of x equal this, be a polynomial function. The following statements are equivalent. So 0, k, your k value is the 0 of the polynomial function. Your factor is x minus k. The solution, k is a solution or root of the polynomial equation f of x equals 0. And our x-intercept, if k is a real number, then k is the x-intercept. All right, so as we're going through this lesson, what they're trying to say is these are very similar. They have things in common. So we are going to graph, and yes, I'm going to graph from scratch. However, when you're in class working on the lesson, you are welcome to use Desmos or the graphing calculator for help. All right, so they give us this equation. By now, we should notice that this is in intercept form, also known as factored form. They use both words. So why is it called intercept form? Because I know my x-intercepts by just looking at this equation. So that's where we're going to start. We're going to plot the points corresponding to the x-intercepts. So remember, this is in the form of f of x equals a times x minus p, x minus q. So if you remember, then we have to do the opposite. So this is going to be negative 3 comma 0, and that means this one is 2 comma 0. So we are going to plot those points on our graph in just a minute. All right, so now we need to plot points between and beyond. All right, so we know we have negative 3 comma 0, and we know we have 2, 0. So we're going to find some other values in between. This is a point I always get asked this question. Where did you get the numbers from? I made them up. What are some x values in between negative 3 and 2? We have negative 2, you can have negative 1, you can have 0, you can have 1, like there are multiple ones. So we could say negative 1, we could say 0, we could say, let's say 3 for this one. So then how do you find the y values? You substitute in the x value into the equation and solve for y. All right, so if I substituted in negative 1, I would get positive 2 times negative 3, and if I multiplied that to this, I would get a 1. So when I substitute in, am I right? I don't know. Let's do the math. Sorry, I'm trying to do math in my head. So if we take 1/6 and we multiply that by negative 1 plus 3, negative 1 minus 2. We have 1/6 times positive 2 times negative 3. Well, 2 times negative 3 gives us negative 6. And if I multiply any fraction by its reciprocal, it equals 1. So negative 1, negative 1. All right, I had to pause it for a minute because I had a mistake and I couldn't figure out where it was. I totally forgot to bring over the square. So negative 3 squared is 9, so that changes our answer. Okay, so let's go back. I got ahead of myself. So negative 3 squared is 9. 9 times 2 is 18. So, and it is negative. So we can look at this as negative 18 over 6. Well, if you divide that, what do you get? Negative 3. So when x is negative 1, y is negative 3. What happens if we substitute in 0? I'm going to do the work for that up here. So we have 1/6 times 0 plus 3 0 minus 2 squared. All right, so this just means you have technically two 2's. So with it being squared, so technically we have 3 x-intercepts, but it intercepts at the same point. All right, so let's work this out. We get 3. Negative 2 squared would give us 4. 3 times 4 is 12. So 12 times 1/6 would be the same as saying 12 divided by 6, which is 2. So when x is 0, y is 2. All right, and last one, 3. I'll put that one down below. We'll come right here. Sorry, had somebody at the door. Okay, so last one, we're going to plug in 3. So we have 1/6, 3 plus 3, 3 minus 2, and squared. So 3 plus 3 gives us 6. 3 minus 2 gives us 1. 1 squared is 1. So 1/6 times 6 would equal 1. All right, so now we're going to graph these points. So we're going to come over here on our graph. We're going to go to negative 3, 0. We have negative 1. Is it supposed to be negative 3, lady? Oh, no. Oh, my goodness. Quit making mistakes. I'm so sorry. I am awful. Right here. So negative 3 squared is positive 9. So this should have been a positive. I am so sorry. It's been a long day. And I don't want to start over. Okay, so this should have been a positive 3, not negative. That negative 1 is a doozy. See, us teachers make mistakes too. It's okay. All right, let's start back. So we got the negative 3, 0, negative 1, 1, 2, 3, 0, 2, 2, 0, and 3, 1. All right, so we now have our points plotted. So what do we do next? So step 1, we plotted our x-intercept. Step 2, we graphed some points. Now we need to determine where our graph should end. So you learned this in lesson 4.1. All right, because f of x has how many factors? All right, well, let's look. We have a square here and a 1 there. So that tells us there are 3 factors. So you're looking at the exponents if you want to make a note of that. Of the form x minus k. And a constant factor of 1/6. So that's our a value right there. F is a cubic function. So because, and this was from lesson 1, so because it has 3 factors, it's a cubic function. With a, so our leading coefficient is positive, so with a positive leading coefficient. So what does that mean? That means that my graph should be going down on this side and up on this side because it is a odd and positive. All right, so what is our end behavior then? Well, the values in this quadrant are negative, negative. So as f of x approaches negative infinity, x approaches negative infinity. Well, what are the ordered pairs in this quadrant? They are positive, positive. So as f of x approaches positive infinity, x approaches positive infinity. So now we know where our graph should end. And so we're going to draw the graph so that it passes through the plotted points and has the appropriate end behavior. Now, we're not going to make straight lines. We're going to make curvy lines. All right, so this graph, we're going to say it's coming down here, and we are going to curve it like that. So don't make straight lines. Make them a little curvy. And there you have your graph. Yes, it's a lot of work to plot a graph from scratch. What you should know, though, is this right here. So you should know where your graph ends based on what we learned in lesson 4.1. You should determine what your graph looks like by knowing how many factors and if your leading coefficient is positive or negative. So that alone should help you have an idea of what your graph looks like. We did this to get specific points. So I have some self-assessment questions. If you're in class, I would say graph these because some of y'all like to watch the videos in class. If you're at home, or what I was saying is in class, graph them on the calculator. If you're at home, open up Desmos, give it a graph. But before you do that, let's talk about the end behavior. All right, so what should your graph somewhat look like based on the information that we know? All right, well, we know that there is this, if there is none, there is one. So we know it has 3 factors. And then our leading coefficient is positive. So we know that it is positive and odd. So knowing those 2 things alone tells you where your graph should end. All right, so just knowing that, we know that our graph picture is going to look very similar to the one before. Our end behavior is going this way, end behavior is going that way, and it's going to curve somehow in between. I'm just graphing for fun, I don't know. I guess like we could say this was -4. I guess I should have kind of come over a little more and made it 1 because we do know our x-intercepts. So in this case, our x-intercept is -1, 0, and this one is 4, 0. So it wouldn't look, well, I guess this could be 4. But, so I just want you to know what the graph should look like. You should be able to narrow it down just by knowing this information. All right, so looking at the next one. All right, looking at the next one. We have 1, 2, 3, but these are all x-intercepts. So we're going to have the x-intercept -2, 0, 1, 0, and 3, 0. So those are all x-intercepts on our graph. Right, so you could roughly sketch a graph just knowing this information. So we got, say that's -2, this is 1, it's 3. You can always find the y-intercept by plugging in 0. So if we did that, we would get what? 2 times -1 times -3, which is 2, 6. So 1/4 times 6. So 6 fourths, which is the same as 3 halves, so 1 1/2. So your graph would cross somewhere here. We know that you have one here, we have a point here, and we have a point here. Where should your graph end? Where's the end behavior? Well, we have 3 factors, right? And our leading coefficient is positive, so it is going to end going this way, and it is going to end going this way. Again, this is from lesson 4.1. So our graph probably looks something a little bit like this. I can't believe I'm doing this in pen, but you know, whatever. So our graph probably looks something along those lines. All right, so if you want to put it in Desmos, see how this one's more accurate than this one because I didn't do the x-intercepts on that one. But you should have an idea of what your graph looks like. I didn't realize there was a second one right here. If you want to have an extra one, I will graph it real quick just so you can have an extra example. Or was that the second one? Oh, that's this one. No? No. Okay, never mind. There was an extra one in here. Don't know where it came from. Why does it look the same as the... All right, I'm pausing. Throwing me off. All right, so if you would like to have another example, I'm just going to do this one real quick just so you have the example. I encourage you to give it a try and come back and match it and see how well you did. So since I didn't really tell you to pause the video on the self-assessment ones, you could on this one and give it a try. And follow the steps from the first question. Okay, so just so you have an extra example, we know it has 3 factors, so and our leading coefficient again is positive. They don't really give us many different examples. So our end behavior is down here and up there. All right, let's talk about turning points. All right, so turning points is exactly what it sounds like. Where does your graph turn? So for example, right here, it stops increasing and starts to decrease. This one stops decreasing, starts to increase. So these are your turning points. So this would be considered a maximum, this would be considered a minimum. However, you are going to be asked for local maximums and local minimums. So what does that mean? So the y-coordinate, now that's important to keep in mind. So remember, y is this way. So the y-coordinate of a turning point is a local max a local maximum of the function when the point is higher than all nearby points. So in this example, this would be your local maximum. All right, that would be that one. All right, the y-coordinate of a turning point is a local minimum of the function when the point is lower than all. So this one would be, that one would be your local minimum. A turning point of a graph of a function is a point on which the graph changes from increasing to decreasing or decreasing to increasing. So just like I said, here is some more information that I thought would maybe helpful that they gave you. In everyday life, turning point refers to a point in time to an event that changes the course of an action. So you could relate that idea to this. So turning points of polynomial functions, the graph of every polynomial function of degree n has at most n minus 1 turning points. So for example, if your degree was 4, 4 minus 1 would be 3, so it should have 3 turning points. If a polynomial function degree n has n distinct real zeros, then its graph has exactly n minus 1 turning points. So whatever your n value is, you take 1 away, you should get the turning points. All right, so example 2, finding turning points. We're going to use technology, graph each function, identify the x-intercepts and the points where the local maximums and local minimums occur, determine the intervals for which each function is increasing or decreasing. So I'm going to do one on the graphing calculator, and then I think I'm going to start a new video and do the rest through Desmos. We shall see. I may do all of them on the graphing calculator. Okay, so looking at A, they told us that if we take our highest degree and subtract 1, so in this case it would give us 2, that's how many turning points we should have. So I am going to type this one in here. How did I get to here? You hit y equals. Okay, so let's graph it. We said that we think there should be 2 turning points, and it looks like there is. All right, so what did the graph tell us to do? We need to identify the x-intercept. So I'm going to zoom in. So I'm going to hit the zoom button, go to zoom in, and hit enter, enter, and it will zoom in for us. All right, so this will help us with some. I need to see a little further up here for one of the turning points, but we can see that the x-intercept is right here. It's a little left of -1. And if you want to know how to do that, just you click on window, the window button right here, and you can change it to whatever you want. So like I made my x minimum 7, my max 5, my y minimum -5, and the max 10, so that way I could see it all. All right, so we want to know what is this x-intercept because we see that it is clearly not on the -1. How do we do that? So we are going to hit the blue button because we want that CALC, calc. All right, so then we're going to scroll, and y'all could make notes of this, like how to use the calculator for this, because you get to in your mastery check. Hit enter because we want the zeros. Remember, zeros are your x-intercepts. See how it says left bound? So you want to scroll a little bit to the left of this point, right? Because if we looked vertically, it would be a little bit to the left of this, and hit enter. Notice how, well, you can't really see. There's like a little line that it put here. You can see that little arrow right there. So it drew a line there. And then my right bound, I want to go a little to the right of the x-intercept, and then I hit enter. See how it now says guess? I want it to guesstimate what my x-intercept is. So I hit enter, and it tells me that my 0 is -1.195823. That is when y is 0. So that is our only x-intercept. So for A, I don't want to use the color pencil. So for A, our x-intercept is, we're going to round, well, let's just round to tenths place, so -1.2, comma 0. All right, that is the only one. So what else did we need? We need the local maximums and the local minimums. So we can see this one. This is our maximum right here. That is when x is 0, 1, 2, 3, 4, 5, 6 is y. So I'm just going to put local max is the y value, so 6. Oh, I just wrote y. Oh my goodness. Y'all are going to love this lesson. Is 6. All right, we need the local minimum. So what is our lowest? And I'm using the y value. Remember, these you use the y value. So I can see that it is right here. So that is up 1, 2. So that is when my y value is 2. So my local minimum is 2. All right, what else does it say that we need? When is our function? Determine the intervals for which each function is increasing or decreasing. All right, so I'm going to write here increasing, decreasing. This you have been doing since lesson 1.5, but we still struggle with it. So our graph increases until it hits the local max. What is the x value here? It is 0. So we would say that our graph increases from the left of 0, which is when x is less than 0. All right, it increases again once it hits this local minimum, which is when x is 2. So we would say when x is greater than 2, because it's going from 2 to infinity. The only time it's decreasing is right here. It decreases from 0, where x is 0, to where x is 2. So we would say in between 0 and 2. So with these, you may need to make a note to use the, so with these you are using the y value. Oh, we can't really see that. Use the y value. And with these, you are using the x value. Okay. All right. I'm going to type in b into my graphing calculator and see what that looks like. I will come back with the graph. Okay, so I typed in the equation. And when I hit graph, because of my window before, I can't see it. So if you need to fix it, you're going to hit window and fix your windows. So let's start off with negative 20, 20, then negative 20 and 20, and hit graph again so if we can see it. Oh wow, so there's a turning point like way down here. So we're going to have to zoom in but make our y value lower. So right now, how many times does it cross the x-axis? It does 3 times. Remember they said to take the highest degree and subtract 1, and that would tell you your turning points. Well, in this one we had 2 turning points. Now if we subtract 1, we have 1, 2, and there's one like way down here, which makes 3. All right, so we're going to answer all these questions again. We need to know where our x-intercepts are. So we're going to do the blue button. So second, calculate. We want the 0. All right, we want the left bound, so we're going to go to the left point. That looks good, so equal. And then let's go to this point and hit enter, and we want it to guess. So it is telling us right here that one of ours is 0.28. So let's round, make that 0.3. All right, so I'm going to write B here. Our x-intercept is that positive or negative? Positive. 0.3, comma 0. So that is one of them. All right, now we need to find another one. So we're going to do the same thing again. And we can do a starting left bound there. And then scroll to the right of it. That should be good there. Hit enter. And, oh, did not mean to hit that button. All right, got to do it again. I'm sorry, I hit the wrong button. All right, we want the 0. And I want this intercept, so I'm going to start about there. and then come down a little bit and hit enter there. And guess, yes, hit enter again. It tells me that my 0 is 1.81. So I'm going to round to tenths place, and so my other x-intercept would be 1.8, comma 0. All right, and we have one left. So that one looks like it's going through 1, 2, 4? But let's see for sure. All right, so let's go over just a little and hit calculate R0, and we want it there, and then we want, that'll work, and there. Yes, we wanted to guess, and it isn't what I thought it was, so it's a good thing I did that. So this would be 5.03. Since it isn't exactly 5, let's go to hundredths place. So for this one, let's put 5.03, comma 0. So those are all three of your x-intercepts. All right, now we need the local maximum and the local minimums. All right, we have a local minimum here, we have a max there, and we have a local minimum there as well. All right, so if you're not able to see it, we can do the same thing we did before, but now we want this as a minimum. So we're going to hit second, calculate, go to minimum, and do the same left and right bound. So we're going to go a little to the left of the minimum and then scroll a little to the right of the minimum. And yes, we want it to guess. Now remember that when you're using your minimum and maximum values, you're talking about the y value. So we're not looking at this value, we're looking at this one. So we could round that to tenths place and say that that local minimum is negative 6.5. All right, so we got our minimum is negative 6.5, so that is one of them. All right, we'll find the other one in just a minute. Let's just go in order. We have a maximum next. So we're going to do the same thing to find what our maximum value is there. So second, calculate. We want to know our maximum value. So we can start where we are. Now we want to scroll to the right of it, so that looks good. And yes, we wanted to guess. And so they're telling us in this case it's 5.1. So our local maximum is 5.1. Okay, now we did have one way down here. We can't see it, but I bet you we could still calculate it and it would tell us where it is. So let's give that a try. All right, we're gonna, oh, nope, that's not what I want. All right, so second, calculate minimum. So let's go right here, and then we're going to end. That's good, right there. And so it does, and it's a good thing because we would be zooming out for a while. So in this case, it is negative 43.0. Just because it's not exactly negative 43, let's put that 0.03 in there. So we would say negative 43.03. So we have two minimums, two maximums. What else do they want? Increasing and decreasing. So when does our graph increase and when does it decrease? All right, so we're looking at the same thing. So what does our graph start off doing? It starts off decreasing until it hits this minimum point. So I should have wrote the x value down because now we need this x value. Okay, we can do that real quick. So second, calculate. We want the minimum just so we can get that x value. All right, so there, and then right bound it right there. So it is, oh, we wanted to guess, yes, so negative 0.57. So we could say negative 0.6. So it is increasing before x hits, or not increasing, decreasing. Come on, lady, get with the program. So our graph starts off decreasing, right, until it hits negative 0.5. So that would be before negative 0.5. Then what does our graph start to do? It starts increasing until it hits this point. So I'm just doing that because I forgot to write down the x values. So we got enter. I just want to know what is the x value of my turning point. And so my x value is 1.1. So remember that was our maximum y value. So our x value is 1.1. So it increases from this point to that point. So we say it's increasing from negative 0.5 to, what is that, 1.1. All right, now what does it do? Now it starts decreasing again. So we could say it's decreasing from 1.1 because we're starting back at that same turning point. And then we need the x value for this minimum. So we could do second, calculate the other minimum, and we want to go from there. And in between there, I guess. So our x value is approximately 3.96. Let's go hundredths just because we don't want it to be 4. So it is decreasing between, what did we say? I don't know why I moved the thing, I'm sorry. So it is decreasing from 1.1 to 3.96. All right, now what does our graph do? From this same point, now it's increasing. So from this same exact one, now it increases. So it increases when x is greater than 3.96. You need to. So this video is getting a little long, so I'm going to stop it here and start a new video.